Imagine filling your car with 50 liters of petrol. Now imagine watching 35 of those liters simply evaporate into thin air before they ever reach your wheels. It sounds like a scam, but that is the reality for almost every petrol car on the road. Less than 30% worth of energy ever reaches the wheels. Most of the energy you pay for is wasted as heat, friction, and exhaust noise. While many manufacturers chased turbochargers for more power, Toyota focused on extracting more work from every single drop of fuel. The result is the dynamic force engine. This wasn't achieved by one big change. It's a collection of dozens of tiny genius tweaks that pushed its thermal efficiency to a staggering 41%. To understand what makes Toyota's dynamic force engine so special, we first need to understand why a normal gasoline engine is so inefficient in the first place. When gasoline burns inside the cylinder, it releases an enormous amount of energy. In theory, all of that energy should push the piston down and rotate the crankshaft, but in reality, that's not what happens. As soon as combustion begins, the hot gases start expanding in every direction. Some of that energy pushes the piston downward, but a large portion immediately escapes into the cylinder walls. Those walls become so hot that they must be constantly cooled by circulating coolant. Without it, the engine would destroy itself within minutes. Even after pushing the piston, the exhaust gases still leave the cylinder at temperatures of 600 to 900 degrees Celsius. That means a huge amount of energy simply exits through the exhaust pipe without ever doing useful work. Then there are the losses you never see. Hundreds of moving parts slide, rotate, and rub against each other thousands of times every minute. Even drawing fresh air into the cylinders and pushing exhaust gases back out consumes energy. By the time all of these losses are added together, only a small fraction of the fuel's energy is converted into useful mechanical work. Now, what Toyota did to increase the efficiency of its dynamic force engine, they started with very simple geometry: bore and stroke. At first glance, bore and stroke seem like nothing more than two measurements, but in reality, they determine how an engine breathes, how much torque it produces, how high it can rev, and ultimately, how efficiently it converts fuel into work. For example, a typical high-performance sport bike engine might have a bore of 76 millimeters and a stroke of just 55 millimeters. Because the piston only has to travel a tiny distance up and down on each revolution, the average piston speed stays low. That massive bore allows engineers to fit huge intake and exhaust valves, letting massive amounts of air rush into the cylinder at high speeds. The result is an engine that absolutely loves high RPM and produces incredible horsepower from a tiny displacement. But a large bore introduces a massive problem for efficiency. The fuel inside the cylinder is ignited from a single point at the spark plug. Because the bore is so wide and the stroke is so short, the fuel and air mixture has less time to spread evenly throughout the combustion chamber, and the flame front has to travel a long horizontal distance to reach the edges. This often results in pockets of unburnt fuel, which simply gets blown out the exhaust as wasted energy. Now let's look at a traditional passenger car engine. A modern, naturally aspirated 2-liter engine, for example, might use an 81mm bore and a 96.9mm stroke. The piston now travels farther every revolution. That longer stroke improves low-end torque, allowing the engine to produce more pulling power at lower RPM. It also creates a more compact combustion chamber, helping combustion occur more efficiently. And today, many modern passenger cars use slightly long-stroke engine designs for exactly this reason. So, what did Toyota do differently? Instead of stopping there, Toyota pushed the idea even further. The dynamic force engine uses an 87.5mm bore and a 103.4mm stroke, making it significantly more undersquare than many of its competitors. Now you must be thinking, why doesn't every other manufacturer just do the same? Increase the stroke length and increase the efficiency? The answer is simple. Everything comes at a cost. A longer stroke certainly has advantages, but it also introduces several serious challenges that become increasingly difficult to solve. The very first problem is friction. Every time the crankshaft completes one revolution, the piston has to travel from the top of the cylinder to the bottom and back again. The longer the stroke, the farther the piston must travel every revolution. That means at the same engine speed, the piston moves faster, increasing friction and putting more stress on the engine's moving components. But that's not the only problem. A longer stroke also changes the angle of the connecting rod. During the power stroke, the rod pushes harder against the cylinder wall, creating a sideways force known as side loading. This increases friction even further and accelerates wear. So, what did Toyota do? Toyota shifted the crankshaft by approximately 10 millimeters relative to the cylinder centerline. This keeps the connecting rod more vertical during the beginning of the power stroke, reducing the sideways force on the piston. Less side loading means less friction, less wear, and more of the combustion energy reaches the crankshaft instead of being wasted overcoming resistance. But friction isn't the only place where energy is being wasted. The crankshaft also loses power driving the engine's own accessories. In conventional engines, both the water pump and oil pump are mechanically driven by the crankshaft. That means they continue consuming power whenever the engine is running, even when maximum cooling or oil pressure isn't needed. Toyota